everyone, it's Michelle here. We are going to have a look at electricity for the end of the year, and in particularly to get better marks and to move up to a level 7 if you are possibly on a level 6. Right, as the base of my presentation, I'm going to be using the examinable content document. Remember, every single one of you should have one like this. It might not look exactly the same as mine. I always use the same one, and you'll see it's scribbled as we carry on. Right, so that's what we're going to use. And the first thing we are going to look at is what do we need to know in electricity. Right, very important is that our electric circuits is mainly grade 11 work. The only difference between the electric circuits is that we bring in the EMF now. Right, so from our grade 11 work, make sure that you revise your grade 11 work. I'm quickly going to just go through what's really important. You must be able to state Ohm's law. That is really important. It is the potential difference across a conductor is directly proportional to the current in the conductor at a constant temperature. Okay. Now that is quite important for you to remember. And what I do is go to, in the back of your book, or in the back of your examinable content, you have your data sheet. Now remember, this data sheet gets given to you in the exams. So what I do is, I go and I write here for myself that this is Ohm's law. Right, and Ohm's law said, if we have a look, it said to us that the potential difference across a conductor is directly proportional to the current. So I go and I write this for myself. The potential difference is directly proportional to the current if the temperature remains constant. Okay, so I've just basically put this in easier words for myself, should I forget the law. And remember, I'm given my data sheet, so this is on my data sheet, and if you write this on your data sheet that you always use, you will remember that this is Ohm's law. And from that, you can see that V is directly proportional to I if my temperature remains constant. All right, okay. So that is the first thing that is really important in this section. Right. The next thing that is important is we must be able to state the difference between ohmic conductors and non-ohmic conductors. Right. Now remember, your ohmic conductors obey Ohm's law, while your non-ohmic conductors do not. Right, we must be able to use this formula for series and parallel circuits and for the maximum of 4 resistors. Right, then another definition that's important is power is the rate of change in work done. Okay, and that formula is on our data sheet as well. So maybe you can just go and remind yourself that that is power. And power is equal to the rate of change of work. In other words, it's work done divided by the time. There are then other formulas that we have here as well. Normally, we would use this one in a series circuit and this one in a parallel circuit. We're going to look at why now. Right, so let's go back. And here we can see solve problems using VI. P is equal to VI, P is equal to I squared R, V squared over R. Right, and then we must be able to deduce that 1 kilowatt hour refers to the use of 1 kilowatt of electricity in 1 hour. And we need to be able to calculate the usage of electricity. Right. Then the work that we actually do in matric, which is very, very little, is we've got to be able to solve problems regarding current, voltage, resistance for circuits containing an arrangement of resistors in series and parallel. And then very, very important, we must be able to explain the term internal resistance. Okay? Right? Something that they've not put here, which I've written here for myself, is we must be able to define EMF. Okay? And EMF is the maximum voltage or the maximum power voltage that a cell can deliver when it's not in use. Right. explain internal resistance. We must be able to solve problems using EMF is equal to V load plus V internal resistance, or that formula. And then we must be able to solve circuit problems. Okay. That is basically what we have to do. Okay. So there's not a lot of definitions to learn. There's Ohm's law, there's power, and then there is EMF and my internal resistance. Right. Now let's just quickly go back to our data sheet again. I don't know if you can remember, I said to you that we normally use this in series, this formula in series, and this formula in parallel. Now, the reason for that is that, remember, we always said that series circuits are current dividers. Potential dividers. Okay. What that basically means is that the total current in a series circuit remains constant. Okay. So, if I have a circuit like this, for example, everywhere here, from here to there, the current will remain the same. Okay. But my potential difference, right, so your current remains the same, but my potential difference will be equal to the potential difference across the various resistors. And to get my total resistance, that is what I would do. Right, so that is in my series circuit. In my parallel circuit, I know that parallel circuits are current dividers. Okay? And my I total is going to be equal to the current across my one resistor plus the current across my other resistor and whatever. And that my potential difference across my parallel resistors will remain constant. Now, this is quite an important thing to remember, people, because we tend to forget this and we tend to get ourselves confused. But when we do a question, we'll go through that. And that is the reason why I say that if we have to calculate power or even work, and we are busy with a series circuit, we will rather use this formula and this formula. Why? Because the current remains the same. Whereas in a parallel circuit, my potential difference across the resistors remain the same. Remember, my current changes. I can use that formula, but then I've got to remember that my current changes. And we tend to forget that. Right, so with this in mind, and with your data sheet next to you, let us look at a few questions. Okay, they say to us, in the circuit below, the battery has an EMF of 12 volts. And an internal resistance of 0.2 ohm. The resistances of the connecting wires are negligible. Okay, so let's just quickly, before we go any further, let's just have a look at this circuit. Here is my battery, my cells, and I know that my EMF is 12 volts. What is EMF? That is the maximum energy these cells can provide. Right, okay. Then I have an internal resistance. At this point, I have an EMF reading. Why? Because my circuit is open. My circuit's not working. So my EMF reading will be 12. It will be maximum. Okay. The minute I close that, my EMF will more than likely drop. And the reason it will drop is because of my internal resistance. Because remember, within the cells, there is work being done. And there is resistance. Right, then I have a connection there, C and D. And over here, very important, can you see here I have a parallel connection? Okay, so I've got to remind myself that the current through the 15 ohm and the current through the 10 ohm resistor, if I add them together, I will get my total current. Now, I also need to remember that the voltmeter reading across my 15 ohm resistor and the voltmeter reading across my 10 ohm resistor will be the same. Then I have In a series connection, I have another resistor of unknown resistance. Okay, so that is the first thing that we're going to look at. Right, the first question they ask here is define the term EMF of a battery. And remember I said to you that was a definition that we didn't have. So let us quickly write it down. It is the maximum energy provided by a battery per coulomb charge passing through it. Okay, right. It is the maximum, and please remember the word maximum energy provided by a battery per coulomb or unit charge passing through it. Okay, and this is normally an all or nothing one, so you need to get it correct completely for 2 marks. Okay, right. I know some teachers say this, and I normally also say this to my learners. It's the maximum energy provided by a battery when the circuit is not working. Okay, but this is a better definition, right? Maximum amount of energy. Right. Now the next thing, and this is quite important, and this is how they test if you know about EMF. Switch S is open, and a high resistance voltmeter is connected across the points A and B. So in other words, a voltmeter is connected over there. And they now want to know from me, what will that voltmeter reading be? And most of us are tempted to say it will be 0, because you say the circuit is open. But remember what happens here. The potential difference across these cells from the one side to the other side is 12 volts. So in other words, this is also going to read 12 volts. Okay? Because the circuit at this stage is not operational. So it will read 12 volts there as well. They're not asking about the current, people. It's about the potential difference. Okay. Then they say to us, switch S is now closed. So now it's closed. And now we go and we connect a voltmeter across C and D. And now they want to know from me, what is that voltmeter reading going to be? Right, now there is my potential difference. What is happening now is the circuit is working. Okay, so across this point, my potential difference is going to be equal to 0. Right, why? Because there is no resistance across that point. Because why? They told me that the resistance in the connecting wires is negligible. Okay. So for that now, it will be equal to 0. I will only have a voltmeter reading across my resistors now, okay, because this resistance is negligible. Okay. And all of us want to do this the other way around. And the reason we want to do this the other way around is because we think of current. We're not busy with current, people. We're busy with potential difference. So it's the maximum a cell can deliver. Okay, if the cell's not working, the maximum it can deliver is 12. Okay, and yet it's not going to deliver anything because there is no resistance. Okay, so question 7.1.2 would have then been that the voltmeter reading will be equal to 12 volts, and in this case the voltmeter reading is going to be equal to 0 or 0 volts. Okay, now when switch S is closed, the potential difference across the terminals of the battery now becomes 11.7. Okay, right, so let's quickly understand this. The EMF is equal to 12 volts, but the potential difference is equal to 11.7. Okay, now, why? Why has this happened? This has happened because I've got internal resistance in my cell, okay? And here it is quite important that we understand When the cell is not working, we refer to it as EMF. And when the cell is working, we refer to it as potential difference. Okay. Now they want to know from me what is the current in the battery. Okay. Step number 1, let us go and look at our data sheet. Okay. When I look at my data sheet, one of the things I see I can use is R is equal to V over I. But I have a bit of a problem because, can you see, I can't work out the total resistance because I have got one resistor that I don't have the resistance for. Okay. Over here, I have EMF is equal to I big R plus I small r. Okay. Now I'm going to write that down and then I'm going to show you how I'm going to rearrange it. Right. So EMF is equal to I big R plus I small r. Okay. I big R, people, is basically V external. And I small r is V internal. Okay? So, that is EMF. What have we got? We've got the EMF which was given to us as 12. We've been given the potential difference, which is now 11,7. So now we can work out V internal. Right. And if we work out V internal, we should get that V internal is equal to 0,3. 12 minus 11,7. Okay. I'm doing this in quite a long way so that you can just understand. Now, can you see, I can now go back here. And I can say V internal, which is 0,3, is equal to I times by small r. And small r was given to me as 0,2. Right, so that gives me I small r. So it becomes 0,3 is equal to I times by 0,2. And therefore, I is going to be equal to 1,5 amperes. Okay. Right, so what do we know now? Now we know that the current in this circuit is 1,5 amperes. Okay. I'm just going to go back and just go over it again. What is the first thing I did? They wanted to know from me what was the current. So I had to calculate I. So what did I do? I went to my data sheet. I looked at this formula. I saw I couldn't use this formula because I didn't have the total resistance. Right. So I went to this formula, and I know that I can rewrite this formula as EMF is equal to V external plus V internal. Okay? So I took that formula, I rewrote it as V external, V internal. I know that this was V external because that was my potential difference. So I could work out my lost volts. Some books refer to it as lost volts. I could work out my lost volts, and once I had my lost volts, I could work out my current. Okay. Right. So now I know that that is my current. Okay. The next question, the effective resistance. The effective resistance through the parallel branch. The words effective, people, basically just means the resistance. Because remember, we're working here with a reciprocate, so it is sometimes not very, very accurate. Right. So, first thing, when I go to my data sheet, I remind myself that I'm busy with a parallel connection. And this is the formula that I use for a parallel connection. Okay? So it becomes 1 over R parallel is equal to 1 over R1 plus 1 over R2. Right, write that down. Then I get 1 over R parallel is equal to 1 over 10 plus 1 over 15. Okay? I find my answer, and then I remember to reciprocate, and R across my parallel becomes 6 Okay. I just want to spend a bit of time here. I don't think it's necessary for me to spend too much time here because I think most of you do understand this. I know there are various ways that people do this. There are fractions over there. My advice is just go and do it properly on your calculator. Go and type in 1 over 10 plus 1 over 15 and then get the reciprocate of it. Okay, remember what you can do is you can go and you can say, right, you've got to get a common denominator. So I'm going to make my common denominator 30. Okay, how did I get from 10 to 30? I multiplied by 3. If I multiply by 3 at the bottom, I must multiply by 3 at the top. So I get 3 plus. How did I get 15? How did I get 15 to 30? I multiplied by 2. If I multiply by 2 at the bottom, I must multiply by 2 at the top. So it becomes 3 plus 2. Okay? So now I get 5 over 30. And remember, that is 1 over r total. So I don't want 1 over r total. I want r parallel. I want r parallel. So I must reciprocate. So it becomes r parallel is equal to 30 divided by 5, which is equal to 6 ohms. Okay. And please, ladies and gentlemen, do not leave your answer like this. Do not leave your answer like that. Okay. Right. So please make sure of that. That was only 2 marks. I think that was 2 easy marks. Now they want to know from me, what is the resistance of resistor R? Okay. There are various ways you can do this. I think maybe let's first go back to our data sheet again. We could go and say, okay, we now know what the current is. We could say, okay, we know what the current is. And because we know what the current is, we can go and we know what the EMF, the potential difference is. We can work out the resistance like that. Right. I personally like to go back to this particular formula. Right. Okay. So I like to go back to that formula. So what do? I write down that my EMF is equal to I big R plus I small r. Okay? We know that our EMF is 12, okay, which is equal to 1,5 R plus 0,3. Okay? Let's just quickly go and see where I got everything. Okay? I got the EMF. It was given to me. Right. What happened to the current? I calculated that earlier. Okay. And I don't know my total resistance yet, so that's what I'm going to work out. Right. And then where did I get the 0,3? Remember, I worked out my internal potential difference earlier on. Okay, I worked that out earlier on. Otherwise, you could have just said 1.5 by 0.2. It would have been exactly the same. Right, so what happens over here now is I solve for R, and I should get that R is equal to 7,8 ohms. Right, let's just double check that. That's going to be 12. Yes, I get 7.8 ohms. Okay, now remember that I only want to know what R is. We've just worked out the effective resistance over here. We've just worked out the effective resistance for my parallel circuit, so that gives me 6 ohms. Okay, so what do I do now? Now I'm going to say R is equal to R total minus R parallel, right? So R is going to be equal to 7,8 minus 6, and therefore my resistance of R is going to be 1,8 ohms. Okay. You could have done it that way, or the other way that you could have done it, maybe some of you would have found this a little bit easier. You could have used the formula V is equal to IR, right? Then you say 11,7 is equal to 1,5 times by 6 plus R, okay? You then solve for R, and you should then get that R is 1,8. Okay. Right, that one looks a lot easier. The maths is just a little bit more difficult. Please remember, people, that in electricity, we do mark with your mistakes. Right. We do mark with your mistakes. Let me just maybe explain to you what I mean by that. Let us say you calculated 1.5 incorrectly. Okay? Let's say you calculated it as 1.8. And when you did the calculation, you substituted 1.8 in here, then you will still get the mark. So what we will do there is, we will look at what that is. And if you substitute that value correctly into the formula, you will still get your mark. You do lose marks for your answers, obviously, but you do still get marks for the correct substitution. Okay, you would have lost a mark for the answer there, but yeah, we would work with your mistake. Okay. So if you had substituted that incorrectly, let's say, for example, once again, you'd calculated your parallel resistance wrong, and you substituted that wrong amount in the correct place, you will still get the marks. Right. Okay. So this was the current electricity. There's still another question regarding power. Let's see if we can see what that question is. Okay. This is now obviously a new question, and the information that we got in the previous question is obviously not applicable to this specific question. So let's quickly have a look here. They tell us, it's also a battery with an EMF of 12 volt and an internal resistance of 0,2. Are connected in series with a very small electric motor and a resistor T. And T has an unknown resistance. The motor is rated X watts, so we don't know what the power on the motor is, and 3 volts, and operates at optimal conditions. Okay. Now, when switch S is closed, the motor lifts a 0.35 kilogram mass vertically upwards at a constant speed of 0.4 meters per second. Assume that there's no energy conversion into heat. And the first thing they want to know from us, what is the value of X? In other words, they basically want to know from us what is the power. Okay. Right. Now let us see what we can do over here. The first thing that you might have to remember is you might have to remember some of your other physics regarding the work done. Now let's just quickly have a look here. Here we have power is equal to work over time. Okay, so we can use that formula. But now you must just remember, how are you going to get your work done? And if you can remember correctly, what is happening here, this 0.32 kilogram mass is being picked up, okay? And it is being picked up at a constant speed of 0.4, and so that is what is happening over there, right? So what I would do in this case is I would most probably go and have a look at my potential difference. Right, it's picked vertically upwards at a constant speed. Okay, so let's quickly see what options can we follow. Right, one option that we can follow is we can use that formula, or going back to our work, energy, and power formulas, we can make use of this formula, right? Where my average power is equal to my force times by my average velocity. Okay, and here you can actually see quite nicely, they've given you your average velocity. They say it's a constant speed. Okay, so what you could have gone and done here is you could have gone and said power average is equal to F times by V average. Okay, right. Now my first question is, can you remember how to get F? And we would have to make use of mg there because of the weight. Okay, so now that's going to become mg times by V average. So that's my power. So my power is going to be equal to 0.35 times by 9.8 times by 0.4. Right, let's see what that gives us. Right. 0.35 and that should give us 1.37. Once again, we round off to 2 decimal places, so it becomes, so my average power, and don't forget the average, is going to be equal to 1.37 watt. Okay, so we can make use of that formula. We also could have made use of the, if we go back here, we also could have made use of this formula, right, to get the W non-conservative, which we would have put up top there, divided by the time. And we would have said it would have been 1 second, so we would have divided it by 1. Okay, so we would have got to the same answer there. Right, now they want to know from me, what is the resistance in T? What is the resistance in T? Okay, what have I got? I've got the power. Okay, you agree with me? I've got the power. What else have I got? I don't have the current. I don't have the current. I could try and work out the current. How could I work out the current? Remember, I have the voltage over here. The voltage over here of the motor, they told us, was 3 volts. Okay, right. So what I would go and do over there is I would go and use this formula. P is equal to VI. So I would have said my power is equal to VI. And I'm busy working there now. Right. Okay. We've just worked out that the power of your motor is 1.37. Once again, can you see I substituted that in there? If I had the wrong answer in there, but I substituted it correctly, I will still get my mark, okay? Which is equal to 3I. Because remember, they told me that this was 3 volts. There it is, okay? So therefore, I is going to give me 1.37 divided by 3, which gives me 0.456. So my current is going to be 0.46. So my current is going to be equal to 0.46 amperes. Okay. Right. Now I still haven't answered the question, because the question was, what is the resistance? Okay, so the next option that I can go to is I can go and I can say that my EMF, remember there are various options you can use, people. I'm going to use this option. We can look at another option just now. My EMF is going to be equal to I big R plus I small r. My EMF was given to me as 12, right? My current I've just worked out as 0.46 times by big R plus 0.46 times by 0.2. Okay? Right. Have we got that? Okay. So now what is going to happen? I can now work out my total resistance. I can work out my total resistance. And my total resistance over here should work out to 25,870. Okay, let's just check. So it's going to give me 12 minus 0.46 times 0.2 divided by 0.46 equals 25. Right, so that gives me 25.87 ohms. Okay? But now remember that is my total resistance. And what is my total resistance made up of? My total resistance is made up of my motor, the resistance of my motor, plus the resistor T. This is total. Okay. So now we know that that is 35,87. Okay, how would I work out the resistance of my motor? I'd have to go back to my formula where I have V is equal to IR, right? So R is going to be equal to V over I, which is going to give me 3 divided by 0.46 plus my total resistance over there. Okay, so let's quickly see if we can work this out. So it becomes, oops, sorry, there's a mistake here. Please take note. And I get that my total resistance, or T, should be equal to 19, let's just check here, 19,37. You see that? So my T is equal to 19,37 ohms. Okay. People, if you look at this mark allocation, it was 5 marks. So that indicated to you immediately that it should be quite a long calculation to get out there. Right, so what I went and did, there are various options you can do. I'll come back to other options now. My first option is I took what I just calculated, which was my power, and I worked out my current. Okay. Then I went to this formula. Okay. I said my EMF was given to me. That was my current times by my external resistance. And remember, my external resistance is made up. My external resistance is made up of this one and that one. Okay? We're going to get to that now. Plus my internal resistance. So I found that my total resistance for the external part of the circuit had to be 25.87. Okay? So this one plus that one had to be 25.87. Okay? Yeah, I had my voltage and I had my current, which was equal to 0.46 amperes, because I worked it out earlier on. So because of that, I could work out this resistance. Okay? So I said, fine, it's my total. This was my total resistance of my circuit minus the resistance of the motor plus, or is equal to the resistance of the motor plus the resistance of T. I solved for it, and the resistance of T was that. Right. The other thing that you could have done is you could have worked with power. Okay? You could have worked with power. And you could have said, let's see if I can, right, we could have worked with power. And you could have said the total power is going to be equal to the power of the internal resistance plus the power of the motor plus the power of T. Okay. To get your total power, you would have had to say, because remember P is equal to VI, so you would have had to say 12 times by 0.46, okay, over here, you would have had to say, how would you get your power here? And you'd have to look which formula you're going to use, okay? Because you are now busy with, right, so you would have just looked what formula you would have used there. Remember, you're busy here with a parallel, with a series resistor, so we'd have to use that one, okay? Right, so you're going to say I squared, let me just write it here, I squared times by R, I squared times by R of your internal resistance, plus your resistor, your motor you've worked out as 1,37, plus I squared R of your T. Okay, so that would have given you 12 times 0.46, 12 times 0.46, which would have given you 5,52, is going to be equal to I squared, and once again I is 0,46 squared times by your internal resistance, which is 0,2, plus 1,37, okay, plus now we're busy with R, with T. So that would have been plus 0,46 squared, because your current's the same everywhere, because it's a parallel, a series circuit, just check, it's a series circuit, right, times by RT. Okay, and then you would have solved for RT, and you should then get the answer of, excuse me, of in the region of 19.37. Right. There are deviations allowed here, people, because of rounding offs and because of different formulas. So if you do not get exactly the same answer, there is a possibility. Normally on the memos, they tell you in what scope you are allowed to be. Right. Ladies and gentlemen, that is electricity. If I can just tell you one thing about electricity. Electricity is practice and practice and once more practice. Remember, on the system, I have given you a whole lot of paper 1 questions. It's questions, your teacher should have given them to you as well. It's a whole document we've set up for you people. Please, you've got to practice those questions. And if you don't understand something in the memo, please go to a teacher or somebody who can assist you. Good luck for electricity.